can move on. So we have seen techniques to discover extrasolar planets. We have seen atmospheres of extrasolar planets. And now we go to the deep interior of extrasolar planets with Jonathan Fortney, University of Santa Cruz.
All right, great. Before we get started, I need to get reimbursed from the University of California for this trip, and I need to prove that I was actually here. So I'm going to take a selfie. Everybody behind me wave. There's my face there. All right, very good. All right. So a number of people have thanked Peter Bodenheimer here today, and I, of course, need to thank Peter Bodenheimer because Peter retired 6 or 7 years ago, and because of that, they were able to hire me. So I really need to thank Peter for that. He's been an excellent colleague, just the next building over for me the past 6 or 7 years. So this is a chapter that we're working on. Isabelle Baroff, Gilles Chabrier, myself, Jonathan Fortney, and Christophe Sautin. This is on the interior structure of planets. And of course, ideally, we'd like to be able to take a planet apart piece by piece and look at the exposed superstructure, or the Emperor's Tower. But of course, a lot of these things we don't actually see. For solar system planets, we can indirectly probe the interior. For extrasolar planets, we can even more directly probe the interior. This is, of course, what we're going to be talking about today. So our chapter goes through a lot of points, a lot of details. I'm going to try to hit on all of those to some degree, but some points I won't be able to go into as much detail. So our main themes are going to be that we're in a new era in the equation of state calculations in lab work. I'll have one slide on that, looking at our pressure, density, temperature relations that we use to model planets. In the solar system, one of the key things is that we now have the ability to look at some long-held working assumptions that we've used in the past. We can test our previous working assumptions to see if they hold or not. We'll also talk about hot Jupiters and the radius anomaly, what causes the radius inflation of hot Jupiters. We'll connect stellar metallicity to planetary metallicity for gas giant planets. And then at the end, we'll go down the mass scale to Neptunes, sub-Neptunes, and super-Earths. And also, we'll talk a little bit about iron in rocky planets. So most of the action these days in terms of exoplanets is in the giant planets, so it's mostly what we'll focus on in this talk. The chapter also focuses quite a bit also on rocky planets as well, but we have to just pick and choose for the talk today. So this is where we were at the time of the last Protostars and Planets. This is from Charbonneau et al., 2007. It says 9 transiting planets. This was the chapter called When Planets Transit Their Parent Star. So at the time of the meeting in Kona, there were about 7 transiting planets. And so this is a scale in Jupiter masses versus Jupiter radii. You can see Jupiter and Saturn. There's HD 209458b. At the time, it was anomalously inflated. And there's HD 159026b, anomalously dense. Maybe it has a lot of heavy elements inside it, a lot of metals. This is where we're at right now. So this is over 200 planets with a mass and radius measurements. This is mass in Earth masses, Jupiter masses, radii in Earth radii, Jupiter radii. I've color-coded the red objects are gas giants, the blue objects are maybe Neptune-like objects, the green objects are perhaps more like super-Earths or in between. The solar system planets are here: Mars, Venus, Earth, Saturn, Uranus, Neptune, Jupiter. I've overplotted lines of constant density, 0.1, 1, and 10 grams per cubic centimeter. So we have a wide variety of densities. Gas giants can be fluffy and tenuous. Gas giants can also be dense because hydrogen is an extremely compressible material. One of the things you should take away from this diagram is the extreme diversity in planets. Jupiter and Saturn only differ in radius by about 15%, but for transiting planets, we can have planets with the same mass differ in radii by over a factor of 2. So something is wildly different about the interiors of these planets. Also, for what you might call super-Earths, and also for Neptunes, we have planets of the same mass differing in radius by a factor of 2. There's much more diversity in extrasolar planetary systems than we have in our planetary system. You can plot models of pure iron, pure rock, and pure water planets. Such things exist, and you can see that Earth and Venus are about 2/3 rock, 1/3 iron. Similar planets exist at higher masses. Also, lower density versions also exist. There's a model for a solar composition gas giant at 10 AU at 4.5 billion years. There's the same model for a planet at 0.02 AU. If you're very close to your parent star, a gas giant has trouble cooling off, and so you get a larger radius at a given age. And so you expect hot Jupiters to be inflated compared to Jupiter, but the magnitude of the effect is much, much larger than anticipated. If you think about Jupiter and Saturn as exoplanets, if you just knew their mass and radius, we could tell that they are enhanced in metals, they're enhanced in heavy elements. That's because they are smaller than the solar composition model at 10 AU. Jupiter is slightly smaller, Saturn's much smaller, so we already can tell just from a mass and radius measurement alone that Jupiter and Saturn are enhanced in metals compared to the Sun, and Saturn is more enhanced. Uranus and Neptune, these objects are 80 to 90% metals, heavy elements, water, and rock. They have a thin skin of hydrogen on top of them. You can also find transiting planets beyond 10, 15, almost 20 Earth masses, Jupiter masses. These things probably, I think, do form like planets. I think core accretion can form these planets this massive. So these are beyond the deuterium burning limit, of course. There's a tremendous diversity, so we're going to explore some of this diversity over the next 30 minutes or so. So my one slide on equation of state, I want to convey how important it is, even though I only have one slide. And so we are in an era now where we have detailed first principles calculations of the equation of state, the pressure, density, temperature relation for planetary materials. We're also in an era where we're doing very detailed laboratory work to validate these equations of state. And this really has been a dramatic advance in the past few years compared to many decades of very uncertain equations of state. So this is the Z machine at Sandia National Laboratory. This is a machine that can take a tiny metal plate and accelerate it to twice the escape velocity of the Earth. And they can crush it into a tiny sample, and they can measure the density, pressure, occasionally the temperature. So there's a very nice new water equation of state by French et al. And so this is density versus pressure. And so the French et al. Equation of state is red line and orange line. And the very precise data from Sandia is red dots and orange dots. And all other older, poorer equations of state are the other colored lines, and older, much less precise data are the white boxes. So here what we have is incredible agreement between a high-pressure equation of states and data. And so what this allows us to do, and now that we have very good confidence in the tools that we're using, our input physics, it allows us to ask more detailed, interesting questions than we could, I think, really do a good job of asking in the past. This is especially important for the solar system, where we have much more detailed constraints. This is also being done for hydrogen, helium, iron, rock. This is just one example, but this is really important for moving the field along. So this is a kind of the standard view of Jupiter and Saturn. I want to go through this for a little while. So these are our gas giant prototypes. We'd like to understand if extrasolar planets are similar to these planets. So Jupiter is about 320 Earth masses. It's mostly liquid metallic hydrogen, which is a state of matter that's a strongly coupled, very dense plasma of protons and electrons. It makes up most of the mass of Jupiter. The envelope we see is H2 molecular hydrogen. Saturn is about 95 Earth masses. It's less massive, so the pressures are lower, so less of its mass is in this liquid metallic hydrogen region. The surfaces of the planets are quite cold, 135, 170 Kelvin. We think the planets are perhaps mostly fully convective, so if you get down to the deeper layers, temperatures are very high, 10 to 20,000 degrees. We know from the galileo-entry probe that Jupiter's atmosphere is enhanced in metals by about a factor of 3. There's no entry probe for Saturn, but we know that the carbon abundance from spectroscopy is enhanced by about a factor of 4 to 10. And so what this tells us is that giant planets are enhanced in metals throughout their envelope. Giant planets are not just a solar composition envelope on top of a rocky core. We think the planets are mostly fully convective, so it's quite possible that this metal enhancement that we see in the atmosphere is true for most all of the interior as well. Jupiter and Saturn are helium depleted in their atmosphere compared to the Sun, so that helium must be made up somewhere deeper down below. I'll talk about this for Saturn just briefly. And what people always want to know is what's the core mass? What's the core mass? So our current constraints for Jupiter are around 0 to 15 Earth masses for simple models, and about 5 to 20 Earth masses for Saturn. I'll talk a little bit about why this might be a more complicated topic than that. But on the whole, Jupiter is about 5 to 10% metals. Saturn's about 15 to 25% metals. So you should think of these objects as being metal enriched. You shouldn't just think of them as being pure hydrogen helium objects. So I mentioned we're at the point now where we can start to examine long-held previous assumptions. So when you derive these constraints on the core mass, you are making an assumption that you have an isentropic, adiabatic, homogeneous envelope sitting on top of a distinct core for both planets. And so it's been discussed for quite a while that that might not really be true, and people have always thought, well, it might not really be true, but there hasn't been a lot of quantitative work addressing this. It's been mentioned before by Dave Stevenson in the 80s, but we are now able, through new techniques, to be able to investigate whether or not this might actually be true. So this is a plot from Wilson and Militzer 2012. This is a plot of temperature in thousands of Kelvin versus pressure in megabars. So the central pressure at the core mantle boundary. CMB is a good way to test what kind of scientist you are. Core mantle boundary, cosmic microwave background. It tells you where you sit on the fence there. So Saturn's about 15 megabars or so. And so this shows you where water, high pressure water, goes from a fluid state to a superionic, more solid state. This also shows you where this ice is unstable versus stable in liquid metallic hydrogen. The point of this plot is to show that Jupiter and Saturn, their icy component of their core, if they have some, is this unstable icy region. So there's no barrier to the ice being dredged up. It's miscible in the hydrogen. It could well be mixed up. So we don't know if that happens yet. No one has done detailed simulations of this mix-up process. It might actually be somewhat hard because the icy and rocky core is quite a bit more dense than the hydrogen, but it actually could be mixed up over time. There's no physics reason we have found yet that that can't happen. And so this paper by LeConte and Chabrier from last year basically looked at a situation where you assume the planets have a composition gradient, which might well happen based on their formation and an early dredge up of their core. And they looked at, is the structure of Jupiter and Saturn today compatible with the composition gradient in the interior? And the answer is yes. You can derive different constraints where you have a slightly hotter interior. You have a composition gradient throughout the whole interior. That leads to a steeper temperature gradient and a hotter interior. So then you need more metals to match the radius of the planet. So you might have convective regions separated by little diffusive interfaces. This is based on some very nice three-dimensional simulations of compositional convection by Garrard and collaborators. So you may have a gradient then in composition and a gradient in temperature that's steeper than just a pure adiabat. And so these kinds of models are the kinds of models that we should be trying to think about and validating and see how well they compare to our current observations. You can also look at this type of model and look at the thermal evolution, because one of the things we can measure about a giant planet is not just its mass and radius and gravity field. We also can measure the intrinsic luminosity coming out of the interior. Planets cool off as they age. And so one of the funny things about Saturn is that Saturn is anomalously bright, especially compared to Jupiter. Jupiter is not anomalously bright. You can fit it with a very simple model that convectively cools over time. So Saturn's known to be too bright compared to a simple black model. So in the past, this has been suggested to be due to helium rain. Saturn's quite a bit cooler than Jupiter in the interior. It might be that helium is phase separating and raining down to deeper layers. That's a topic I've worked on quite a bit. And that might prolong the cooling because you differentiate and get an additional energy source as the helium rains down. What LeConte and Chabrier have looked at, well, if you do have a composition gradient in the interior of Saturn, how does that affect the cooling? Well, the cooling is actually quite a bit slower in that it's harder for energy to work its way out through the interior. And so what you get is at a young age, compared to the black model, which goes way up here to probably about 600 degrees, since the energy is coming out more slowly, you have a cooler starting. Planets are colder at the beginning, but because the energy takes such a long time to come out, they eventually get hotter at older ages. So a perfectly viable explanation for Saturn's internal current effective temperature might be composition gradients in the interior, not helium rain, or you could have a combination of the two. That actually might be the most likely. So these are non-standard models that we are in a position to investigate now because we have new models of convection, and we have nice input physics now that we can now use to investigate whether or not this is actually likely or not. Before I switch to talking a little bit more about some other topics, I want to mention that most of this talk is on transiting planets because we can measure the mass and radius. But direct imaging is also extremely important. So you can see that over here, these planets are quite faint at young ages. And so another potential way to get a faint planet at a young age depends on the accretions. These are models that we published with Mark Marley a few years ago. If you're familiar with directly imaged planets, this is hot start versus cold start. And basically, the early evolution of planets, whether or not they're hot or cooler, depends very sensitively on how you treat the thermodynamics of accretion. And so one of the nice things about direct imaging is that by imaging young planets from 1 to 100 million years, we can learn a lot more about the initial conditions for the structural evolution for planets. And so transits are nice. They tell us mass and radius and density. But direct imaging will also be important to understand the initial conditions that we have for planets. So I wasn't going to talk about this, but I think you guys all should know about Juno, because it's a $1 billion NASA mission, so I decided to slip this in. So Juno is going to Jupiter in about 2016. It is, for the most part, a mission to probe the interior of a giant planet. And so the main questions that Juno's going to try to answer, and it's going to be at Jupiter for about a year, are the observed surface flows representative of the internal differential rotation? We actually don't know if Jupiter rotates as a solid body, rotates on cylinders, or rotates in a more complex fashion. We don't know that. We don't know how giant planets operate in terms of their internal convection patterns. So by examining the gravity field in very precise detail, which Juno's going to do, Juno's going to end up being in a very close-in orbit. It's only going to go about 2/3 of an Earth radii away from the surface of Jupiter. We'll be able to do that. It also has essentially a microwave spectrograph to look down to very high pressures of about 100 bars. It's going to determine the deep water abundance and deep ammonia abundance, oxygen, nitrogen, below the cloud decks. So one of the problems that Madhu mentioned for Jupiter is that it's so cold we actually cannot measure the water abundance just by taking a normal infrared spectrum. The clouds are 10 to 20 bars. And so with Juno, we'll be able to, depending on the error bars, I hope they'll be good, we'll be able to have our first measurement of the water abundance in Jupiter, which probably, to some degree, is the water abundance throughout the whole envelope if it's fully convective. And that'll tell us about the C-to-O ratio for that planet. There's also going to be detailed mapping of the magnetic field. Of course, the dynamo of Jupiter is caused by the convecting liquid metallic hydrogen in the interior. So in principle, by understanding the dynamo in a very detailed way, we can also understand the interior in a very detailed way. There's also some other really cool things that might happen. So there's this lens-throwing frame dragging effect from general relativity, and it's possible that we might be able to actually measure the angular momentum of Jupiter and also get its moment of inertia from this effect. It's also possible that tides raised on Jupiter by Io may allow us to measure this K2 love number, which is a measure of central concentration as well. So one of the things that's hard to do for Jupiter is get a direct constraint on the core mass. And that's because if you measure the gravity field, so the external gravity field can be written in terms of the Legendre polynomials, P sub 2n. These coefficients, J sub 2n, or people just call them the J's, the gravitational coefficients, these are weighted well out towards the surface of Jupiter. So there's very little lever arm in terms of measuring the actual core mass. But in principle, if we can understand the envelope very, very precisely from the gravity field, that'll indirectly tell us more about the core if we understand the envelope as precisely as possible. Also, a lot of the same physics is going to be done for Saturn, particularly for the gravity field. That's going to be done for Saturn by the Cassini extended mission in 2017 as well. So that'll also be a nice data set. I myself haven't really worked much on the gravity field of the planets, but Yohai Caspi, Ravid Haled, Bill Hubbard, and Jerry Schubert are doing a lot of nice work recently on that. So thinking about Jupiter and Saturn, we know they're enriched in metals. That's kind of unavoidable now. But given that we don't really know if the current structure, if we do derive a current core mass, we don't really know if that was the original core mass or not. That's something we're working towards, but we're really unsure of that. And so I think going forward, it makes we shouldn't worry as much about what's the core mass versus the envelope mass of metals. We should think about the total abundance of metals within the planet. And that's fine, that's not a problem, because for exoplanets, which we want to compare to, the only thing we're going to measure is the total abundance of metals. Except in very rare cases, I doubt we'll ever get a measurement of the core mass of an exoplanet. We're just going to know the total abundance of heavy elements. So it makes sense to think about Jupiter and Saturn in terms of their total heavy element mass as well. So Jupiter is about 3 to 10 times solar in metals. Saturn's about 12 to 20 times solar. And these are the constraints from a simple adiabatic model, which we can, even though it's uncertain if the partitioning is mostly in the envelope or mostly in the core, the total abundance of heavy elements is reasonably well constrained. It'll become better constrained in the future. So I want to move on and now start talking about comparing these planets to exoplanets. This is a plot from Dave Spiegel showing radius in Jupiter radii versus incident flux upon the planets. So we've got solar system planets, Mercury, Jupiter, Saturn, and we've got color-coded actual confirmed planets with a mass measurement. We also have Kepler KOIs and open circles. So there's lots of Kepler objects down here. But what I want you to notice is that generally the hottest of the hot Jupiters, the ones that receive the most incident flux, tend to be the largest radius planets. This is really something we've only really appreciated, I would say, in the past 3 or 4 years or so. And as you get to cooler objects, they're not inflated or much less inflated. We'll come back to that in a minute. So any sort of explanation for why hot Jupiters are inflated has to explain this general trend. So there's different classes of explanation. There's a lot of text on here, but we'll get through it. So the different energy sources, I would say, are energy that comes from the star, energy that comes from the planetary orbits, and other mechanisms that delay or stall the contraction within the planet. So it's been pointed out originally by Showman and Guillot and other people that if you get about a small fraction of the parent star's incident light, 0.1% to 1%, that light is usually absorbed at about a bar, so it doesn't get to the interior. You have to get the energy down deep to inflate the radius of the planet. But if you can get on the order of this amount down deeper towards the radiative convective boundary at around 100 bars, that amount of energy is enough to inflate a radius of a planet from about 1.2 Jupiter radii to perhaps 1.7. You need to get the energy deep down. So a mechanism like this that uses energy from the parent star readily explains the strong correlation with incident flux. The hotter planets have a larger incident energy source upon them, so perhaps that's why they're more inflated. What we're really missing right now is the mechanism for energy conversion and deposition deep in the atmosphere. So I'll talk about a couple mechanisms next. This plot over here is the radius anomaly. This is the excess radius in Jupiter radii versus planet mass from a paper from a few years ago. So it happens for a wide variety of planets. You could also have energy coming from the planetary orbit. There's a lot of energy there as well, perhaps from tidal energy deposition from eccentricity damping. That works well because it is an energy source, but it's quite short-lived, as I'll talk about next. And it really, the consensus now is that it cannot be the universal mechanism. There's also potentially delayed or stalled contraction. If you have high atmospheric opacities, that could slow the contraction, but it's not a large enough effect. You potentially also could have composition gradients that could stall cooling and stall contraction. And that might happen in some circumstances as well, but it's probably not the universal mechanism. So tidal inflation, there's been a tremendous amount of work on tidal inflation. Over a dozen papers, I would say, over the past 10 years. It's a very attractive mechanism. But most recently, LeConte et al., using perhaps, I think, the most sophisticated tidal evolution model, have shown that, well, in some instances, you can inflate planets. It's easiest when they're young. If you want to inflate objects at old ages, billions of years, it just really doesn't work. So here's a tidal model where they look at the semi-major axis decay, the eccentricity decay, the radius evolution, and the tidal power. And just generally, it does not work to inflate objects at old ages. And so this really cannot be the universal mechanism, although it may play a role in inflating objects when they're very young if a lot of hot Jupiters come in via tidal circularization. It's not the reason why planets are inflated at old ages. So I want to talk about two contenders, potentially, where energy comes from the parent star. I can't spend a lot of detail on these, but there's a lot of papers, so I think you could certainly investigate if you want to as well. So one I think people have probably heard a lot about, potentially, is ohmic dissipation. This is first from a paper from Badigan and Stevenson, and also from Perna et al. Around the same time. The basic idea, there's a lot of work up here. The basic idea is that if you have a planet, it has a dynamo, okay? It has its own dynamo, B field, coming from the interior. But these strongly radiated planets also have very fast winds running along the surface. That we observationally can tell. If the planets are hot enough, beyond about 1,000 or 1,500 degrees, it's hot enough that you can actually thermally ionize, alkalize sodium and potassium, which are fairly abundant. So what you get then is that these thermally ionized alkalis are being advected around by the winds. So you essentially have ions flying around in this wind. So that creates a B field distinct from the internally generated B field from the dynamo. So the associated current given by this B field is actually driven into the deep atmosphere. It's not necessarily clear if it makes it all the way down into the deep interior, but it's actually advected. It's created much deeper than the 1 bar level. So the photons are absorbed by about a bar, but they drive this wind that can penetrate to tens or even hundreds of bars. So it's a way of getting the energy that wasn't photons into kinetic energy into the deep interior. So this current then that's created ohmically dissipates in the resistive interior with some power that's about J squared over sigma, the conductivity. And so there's been a number of papers trying to quantitatively estimate the amount of power that you have here. This is a paper from Wu and Lithwick this past year. The real planets are in blue. The theoretical planets, making some assumptions, are in red. And so what they generally find is this general trend that the hotter of the hot Jupiters tend to have the most inflated radii. And so it looks promising. That's about all we can say right now. More work needs to be done, but it looks promising. Real planets are, of course, down here, because these model planets are all pure hydrogen helium objects. Real planets are enhanced in metals, which we'll come back to. Another contender is the thermal tide. This has not been looked at in as much detail, but I think it's promising, and I think other workers should look at this. So far, it's really only been investigated by Eris and Socrates and Jeremy Goodman as well. Gu and... I'm sorry, one more paper. I should have put it on there. Basically, the idea is that the thermal tide generally occurs on planets due to finite thermal inertia of the atmosphere. So we experience this on Earth. It's not hottest at high noon. It's hottest in the afternoon. So that's a thermal tide. And so what can happen is on a hot Jupiter, this is the substellar point here that's facing the star. But what happens is that it's hottest not at high noon. It's hottest later in the day. It's hottest over here. That's the hot point. So what happens is that you have hot point there, but you actually get a cold spot over there. And the cold spot is denser, so it actually works almost like a bulge. It's a denser part of the planet. So what you get is a cold spot, this thermal tide, and the tides raised from the star act to pull this bulge along this line connecting them. So that's what's trying to happen based on the thermal tide. But of course, there's an actual gravitational tide in green, and that works in the other direction. So you have a thermal tide and a gravitational tide opposing each other. And so the outcome, perhaps then, is the planet's driven into a slightly non-synchronous rotation permanently for a very long period of time. And so the outcome is that you might get a long-lived tidal energy source where the energy is due to the star itself. It's not due to the orbit per se. And so this is a model on AstroPH very recently, looking at the radius anomaly versus a measurement of the thermal tidal power. Black are real planets, red are model planets. But I just want to mention this is another possibility. But the main idea is how do we get energy that's absorbed at 1 bar down to deeper to 10 or 100 bars. So real planets are, of course, smaller because they're enhanced in heavy elements. So I want to spend a couple slides thinking about connecting planetary metallicity to stellar metallicity. So this is planet radius and Jupiter radii versus incident flux. So Earth's over here, very cold planet. This is color-coded by temperature. And so what you can see is hottest of the hot Jupiters are the most inflated. But once you go beyond about 2 times 10 to the 8th, which is about 1,000 degrees, you see the radius anomaly ends. And so any theory for what inflates hot Jupiters has to explain why this ends at about 1,000 degrees. But what's interesting to me is that beyond 1,000 degrees, none of these planets are inflated. They're all smaller than this green curve. This green curve is a solar metallicity object. So all of these planets, no matter what their mass, because they're smaller than this line, they are enhanced in heavy elements, they're enhanced in metals. And so we can start to think about connecting the planetary metallicity to the stellar metallicity. So this has been looked at previously by Guillot and Burrows et al. But they had to make an assumption for what was causing hot Jupiter inflation. Here we're looking at cold planets, and the assumption basically is that there's no excess internal power. And so we can derive the heavy element mass in Earth masses versus stellar metallicity. We're basically taking the planet's known mass, its radius, its age, and we're running a whole suite of evolution models and figuring out the model that has the correct heavy element abundance to match its radius at its known age today. And so there's a couple interesting things. One is that it looks like, I think there's some error bars, of course, but there's some pretty good evidence that all hot Jupiters, or maybe perhaps all giant planets, need to have something like 10 to 15 Earth masses in their interior. And then when you get to more metal-rich parent stars, you get more metal-rich planets. That's been suggested previously. This is a sample of only about 14 planets. So another way to cut this is looking at heavy element mass and Earth masses versus planet mass. And you can use different colors from metal-poor stars, slightly metal-rich, even more metal-rich. And you can compare the amount of metals for these planets versus Saturn. So this is Saturn and its cousins. This is Jupiter and its cousins. You can also plot Z planet divided by Z star. So the Z planet comes from the model. Z star comes from the Fe over H. You can look at the metallicity enhancement of planets. So you can see Saturn compared to its cousins fits in quite well. Jupiter compared to its cousins fits in quite well. And the same pattern we see in the solar system, that as you go to lower mass planets, you have a higher metal enrichment, is found in extrasolar planetary systems as well. And you can imagine cutting this a lot of different ways. This is based on 15 planets. This sample of cooler transiting planets is now about 30. And you can imagine in the future basing this not just on Fe over H, but Si over H, O over H. You might actually learn something about what the heavy elements are within the planets by looking at different stellar metallicity bands. You also might look eventually at close-in planets versus further planets, or you could cut this when you have a larger sample size of metallicity of M-star planets versus F-star planets. There's a lot of ways you can cut this once you have a larger sample size. So I think there's a very bright future in connecting stellar metallicity to planetary giant planet metallicity. So I want to switch gears to some lower mass planets in the last 5 minutes or so. Uranus and Neptune are not nearly as well understood as Jupiter and Saturn, I would say. We know they're about 80 to 90% metals, heavy elements by mass. Simple models tend to have a hydrogen-helium envelope with some other ices, convecting envelope. The temperatures, again, are high pressure, high temperature. But the things we really don't know are, what is the interior like? Is it fully convective or not? Neptune's intrinsic flux coming from below is 10 times larger than the intrinsic flux from Uranus. So they may well have very different interior structures. We actually don't know their ice-to-rock ratio. If you compute models where you just have hydrogen, helium, water, and rock, you often can find water-to-rock ratios of 10 to 1 or 20 to 1. But we don't really know that that's true, because if you're building a model of an ice giant, you can always take a little bit of water away and then add more rock and more hydrogen and get a very similar model. So we're blind, really, to the ice-to-rock ratio in those planets. They may well have composition gradients, which might inhibit the cooling of Uranus. So we're not really on the best footing when we're trying to understand exoplanets of similar mass, just because we still don't really know what's going on beneath in Uranus and Neptune. This is a plot of mass versus radius for these low-mass, Neptune-like, and sub-Neptune planets. This is radius in Earth radii, planet mass in Earth masses. These are curves of a very iron-rich planet, a pure rock planet, a pure water planet. This is a rocky object with a 1% hydrogen-helium envelope and a 10% hydrogen envelope by mass. So you can see Uranus and Neptune are up here. This is color-coded by how hot the planet is. This is incident flux compared to the Earth's incident flux. There's a lot of interesting things going on here. We can certainly find low-mass, low-density planets that need to have appreciable hydrogen-helium envelopes, several percent of the planet's mass. That's the only way you can make planets up here. Potentially, you could have some pure water planets, but my bias is that such things don't exist. So these things need to have small hydrogen-helium envelopes. There's also this interesting feature at around 8 or 9 Earth masses where there's really nothing over here. A lot of these objects, More objects than not have hydrogen-helium envelopes. Very few of them, only about 3, are consistent with rocky objects. So one of the things I think is interesting in terms of planet formation is that we might well end up finding a few years from now that 5 to 10 Earth mass objects really commonly have hydrogen-helium envelopes, and that the bare rock super-Earths are actually quite rare. These 3 objects that are true super-Earths, you might call them, bare rock iron objects, these are all in 15-day orbits or less. So they may well have started with hydrogen-helium envelopes, and they've lost them today. So I think we really have to think about super-Earths in the future as perhaps being more like mini-Neptunes that accumulated hydrogen-helium envelopes. That's certainly what I take away from this diagram in this left region over here. Now, these planets are kind of complicated. As you go to lower masses, planets always become more complicated, so keep that in mind. So these H-dominated atmospheres that are a few % of the planet's mass, they are potentially accreted, but it's been pointed out by a few authors that they also might be outgassed from the interior. You could sometimes outgas hydrogen, so it's something to keep in mind. Also, these hydrogen envelopes can evaporate over time. We know that hot Jupiters slowly evaporate over time, but if you're made of 300 Earth masses of hydrogen, the planet doesn't really care. But if you only have a half of an Earth mass of hydrogen, the planet cares if it loses that. You could actually transform the kind of planet you are by losing just a small amount of hydrogen. We also don't really know for these sub-Neptunes what the main component is of the heavier elements. Below the envelope, is it mostly rocks, mostly water? We don't really know that for Uranus and Neptune per se, so of course we don't know it for objects as well. This touches on where they formed, inside the ice line or outside the ice line. And also, one of the things I'm interested in is, are these hydrogen envelopes, are they extremely metal-rich? That's something Madhu talked about for probing the atmospheres. If they are very metal-rich, what are the diagnostics of that? It's probably too simple-minded to imagine a solar composition hydrogen envelope atop a rocky core. That certainly doesn't work for any of our own giant planets in our solar system. I want to mention that one of the ways we might be able to probe what's beneath the hydrogen-helium envelope, in my second or third to last slide, is that for very close-in objects, we might be able to see what's beneath the hydrogen envelope if a planet has lost its hydrogen envelope. So Kepler 36 is a very interesting system. It's 2 planets around a G-type star. One's in a 14-day orbit, one's in a 16-day orbit. The inner planet is a bare rock iron object. The outer planet has an appreciable hydrogen envelope. But they're basically in the same orbit. They're basically in both a 15-day orbit. What we find is that we can start them out both being something like what you might call mini-Neptunes that have a 20% hydrogen-helium by mass. The closer in object is less massive. The further out object is more massive. This object more readily loses its hydrogen as a lower gravity object. The slightly more massive object more readily keeps its hydrogen. So they can have divergent evolutionary pathways. So in this system, perhaps Kepler 36 is showing us that this may be an in situ formation case, because what's below the hydrogen envelope is a rock iron object that's perfectly consistent with an Earth rock iron ratio. So it's possible when we find more of these very close-in objects, we might be able to see, by looking at the remnants, what was below the hydrogen-helium envelope that was there, perhaps when they formed. So I didn't have a lot of time to talk about rocky planets. Our chapter is going to be maybe a quarter rocky objects. I want to mention 2 very simple things that I think we can measure today or else very soon. One is that there's a poster on this by Verm et al. Up over there, that one of the interesting things about Mercury is that Mercury has a very high iron to rock ratio. Earth and Venus are around 2/3 rock, 1/3 iron. Mercury is more like 60-40 or even a little bit higher, more iron rich. And so there's been lots of suggestions for why this might be true. But one of the things we could potentially do is look at extrasolar planets. And this has been suggested that it might have something to do with being so close to the sun. Well, we have versions of Mercury, more massive versions, that are much closer to the sun, not in 88-day orbits, more like in a 2-day orbit. And we can investigate, once we get a larger sample size, larger than 3, we can investigate if close-in super-Earths are actually iron-rich or not. So this is a possibility for answering a long-standing solar system question by looking at extrasolar close-in rocky objects. It's always better when you have a sample size bigger than 1. Another thing people should keep in mind is that we already know a lot about the equation of state of iron. This is a slide I got from Gilles based on Morardidar. And this is looking at the melting curve for iron in red. This is temperature versus pressure. This is an alloy of iron, a little bit slower melting points. But you can see it crosses the interior of Earth at 1 Earth mass planet right here. This is the interior profile of Earth. And so Earth has an iron outer core and a solid inner core. But as you go to higher and higher mass objects, 5, 10 Earth masses, these objects are all well below the melting curve. And so old, several billion-year-old super-Earths should have solid cores. They're not going to have, probably, unless there's a lot of radioactivity, they're not going to have dynamo-generated cores. They're going to have solid cores. So the overview then is that, going back to the first slide, one of the nice things is that we're in a new era of modeling in terms of the equation of state. We have precise input physics, precise measurements, and very nice first principles calculations for the equation of state. The constraints on the distribution of heavy elements within the solar system gas giants depend on model assumptions. We should always keep that in mind if you're assuming it's a very simple model or a more complex model. So it probably makes more sense to think about the total metal abundance of giant planets. The transiting gas giants, there's really no consensus yet on the hot Jupiter radius inflation. Whatever the mechanism is, or classes of several mechanisms may be operating together, they must be based on the level of incident flux to some degree. The hottest hot Jupiters are the most inflated. It's time, I think, to start thinking about giant planet metal enrichment as something that we can try to match for planet formation models. And so the metal enhancement of Jupiter and Saturn is very similar to exoplanets of the same mass. Neptune's and below, there's always degeneracy in composition. Ice-rock ratio unknown, we'd love to know that. And evaporation effects are quite important for these smallest planets. For rocky planets, some fairly simple yet important questions can already be understood, I would say. That's why I mentioned that in that one last slide. And so I think the key is, of course, to keep finding planets. Obviously, we'd like to have a much larger sample size. And so from ground-based observations and from space, and also from imaging for young systems, I think we're really in a very interesting state right now where all of our input physics are the best they've ever been, and we're finding a larger sample size of all kinds of planets. And so I think we're going to start making very real progress in understanding the composition and structure of planets. Thanks a lot.
Thank you very much for this nice overview. So the paper is open for questions. Seth.
Hi, I have a pretty ignorant question, and that's, you mentioned core accretion early in your talk. At this meeting, we've been hearing a lot about pebble accretion. Do you think accreting from large embryos versus small pebbles, does that have any implications for the core in the interior of these planets, and what are those implications, if you've thought about this before?
I'm not sure. Well, I mean, where the core forms in the disk is important. You potentially could have more or less ices, depending if the core formed relatively closer in or further out. It's possible that an icy core might be easier to dissolve into the envelope than a rocky core because the material is less massive. Just in terms of whether it's made out of pebbles or not, probably it doesn't make much of a difference. There's the gravity, the self-gravity of the object kind of, I don't know if anneals quite the right word, but it's going to form a solid object either way. But perhaps maybe in terms of where the core forms might be important, but maybe not in terms of other ways. But I haven't really thought about it before.
Eric?
Yeah, Eric Gaidos, University of Hawaii. Jonathan, thanks again for a really excellent talk. One thing when I look at these mass radius diagrams, one thing we have to keep in mind, a cautionary note, is that our ability to detect these transiting planets also depends on their radius.
Very true, yeah.
Intrinsic biases. These biases are high powers of radius and orbital period. So, for example, you're much more likely to detect the planet with a hydrogen envelope transiting than you are, for example, a very compact rocky object.
That's certainly true.
So it's possible we're just seeing the fluorescent red zebras in the jungle that are so easy to see.
That's a good point. Thanks for mentioning that.
On the left.
Hello, Ian Crossfield, MPIA. So you mentioned Juno and you mentioned Cassini. Are there any prospects for improving what we know, though, about the interior structure and composition of Uranus and Neptune, whether from laboratory or observations of some sort?
Yeah, so in terms of laboratory, there's a lot of really nice work going on now in terms of the equation of state of ices and icy mixtures. So there's no reason to think that the interior is just some water layer. It's probably water, methane, ammonia, fragments of molecules. So people are actually working on what you might call high-pressure chemistry to see how the equation of state of this material might differ from just pure materials. So I think that's very interesting. In terms of more data, missions, I would love that. So there are proposed missions, European missions, to go to Neptune and do an orbiter like Cassini, or to some degree, go to Uranus. I think that would be fantastic. I mean, we really need to know a lot more about these planets. I mean, they're much small. These 15 Earth mass planets are much more common than the gas giants, right? So those missions, I think, would be like 2035, something like that. So it is kind of crazy to think about. It's a long way off, but I really hope something like that does fly. There's a lot of good, science for the moon systems you could do as well.
Next question, please.
Shamila Miguel, MPIA. So I have a question about, because how metal-rich is the envelope of Jupiter was taken with the Galileo probe.
Yeah.
And I seem to remember that I read something that it entered in a very dry area, so that might change actually the idea that we have of the metallicity in that planet envelope.
Yeah, so it fell into a region that's called a 5-micron hotspot. So the cloud coverage is not uniform on Jupiter. So there are regions where you can see fairly deeply into the atmosphere because there's no cloud there, and if there's very little water abundance, there's very little water opacity, you can see deeper down. So people have actually done 3-dimensional dynamical atmosphere modeling of that particular location, and it's thought to be in a downdraft, actually, where you're taking dry air above the clouds and pushing it down. So that affects the humidity of water. So it's been suggested that the water abundance that was measured is actually a lower limit, because the water abundance that was measured was going up and going up and going up, and by 22 bars, when the probe stopped transmitting, the water abundance was still going up. The other abundances of all the other atoms and molecules were essentially constant by 22 bars. So that's, and these cloud processes probably don't affect, for instance, methane or xenon or these other molecules, these other atoms. But it's certainly a big problem for water. So we would love to know what it might be that the true abundance is quite low, but I don't have any confidence in that because the measurement was still going up when the probe died. So hopefully Juno will be able to answer that.
Roman?
Roman Rafik of Princeton. Jonathan, could you please comment on the possibility of planetary seismology with Jupiter and Saturn? Because there has been some recent claims of detecting modes in Jupiter, and there has been also interesting ideas about some resonances in inner rings of Saturn that could be explained by actually resonances with internal modes of Saturn. So what are your thoughts about this?
Yeah, thanks for asking that. I thought about talking about it. Yeah, so there's an instrument built in France called SIMPA, and it's a high-resolution spectrograph made to look for...
It's made in Nice, watch out.
I'm sorry?
It's made in Nice, watch out.
Oh, okay, all right, great.
Not by me.
And so for years, they've been trying to look at light from Jupiter that shows the oscillations of the planets. And so there was a detection.
Claim detection.
A claim detection. All right, sure. The claim detection was basically consistent with almost all available previous models. So that first claim detection is not yet constraining, really, for the structure. But they have accumulated more data, and I'm very interested in seeing what it says. Because in principle, it's very complementary information to the gravity field information. For Saturn, this is perhaps even cooler. So it's been suggested by Mark Marley about 25 years ago that Saturn's rings may act like a seismograph. So most of the features in Saturn's rings are due to shepherding by moons. But there are features in Saturn's rings that are not due to any moons. And so those looks like they're potentially due to oscillations of the planet itself, moving mass within the planet, moving the rings. So the locations of those gaps are actually very similar to locations predicted invented by Mark Marley in 1990. The weird thing is that they're split. There's not just one. There's weird splitting of 2 and 3 features, and so that was totally unexpected, and no one knows what to make of that at all. So I do think it will be very valuable, and something people have hoped for a long time, but I think it's going to be extremely complex, and so there's no obvious thing in terms of what we're going to learn.
Could it be rotational splitting?
I don't think so. That was already included in the calculations. So it's some sort of, it might be some sort of differential rotation splitting or something like that. Maybe, I don't want to say too much. But there are people who are coming from the helioseismology community now thinking about this, and they have obviously very sophisticated modeling approaches, so I'm hopeful we can make some progress with that.
Thanks a lot for exhaustive answer.
Sure.
Question?
Hello?
Yes.
Hi, this is Feng Tian from Beijing, China. Beautiful talk. If you go back to the slide when you talk about old super Earths may not have a liquid core.
Yeah.
That I'm very interested in that. Can you say some more about the conditions? For example, what if the super Earths have more water content, and how will that influence the result?
I am not an expert in that particular area, so I really. So this plot is an equation of state plot with models from Valencia et al. 2007, which I think was like an Earth-like composition, and Soten et al. 2007, looking at this core mantle boundary here, here, and here. And so I can't really speak to the details. You'd have to look at the assumptions made in Soten and in Valencia. I'm not sure. I think they used, what they tried to do was essentially as close to Earth-like conditions as possible, so I'm not sure.
Okay. So I have maybe a final question. In this debate of whether super Earths form locally or further out and migrate in, so of course the composition is key, but you showed that composition can change. The planets can lose their hydrogen, helium envelopes, ices. So is there any hope in the future from this kind of measurements and modeling of interior structure to really discriminate between something that forms rocky, probably in situ, in a hot part of the disk, from something that might be thin from further out?
That is a $64,000 question. Yeah, I've thought about that a lot, and it's hard to say. So one of the things I'm interested in is atmospheric enrichment in the hydrogen envelope. It might be that objects that form farther out and then have to migrate in, maybe they would see more planetesimals or less in terms of their enrichment that they get in terms of their atmospheres. So we might see differences in that case, or around M stars versus G stars, for instance. In terms of these remnants, I don't know, I think this is potentially interesting in that, so 55 Cancri E, this is a really hot planet, and it can't be a rock iron object. It's too low of a density. So it has been suggested that it could be the remnant of a watery rock object with a little bit of water left. It's hard to tell. I think given that it seems like evaporation is important, we need to really understand evaporation much better than we do today in terms of the mass loss rates and how it might differ for a metal-rich atmosphere compared to a hydrogen atmosphere. I think we can get something useful, but it's not going to be in a year. I think it'll take a while.
All right, great. Thanks a lot.